Welcome back to using containers in bioinformatics today, and that you're ready to build on your skills. I'm Christina Hall from the Australian Bio, and again today we have Anne Backhouse from Pawsey Supercomputing Centre making the systems work. Marco de Pierre will be guiding us through the content and providing answers to your questions along the way. Our facilitators are back, and you'll hear more about their experience using containers today. This team of volunteers is spread out far and wide across Australia and New Zealand, and it's no mean feat to bring such a it's great that they're willing to offer their help to an international audience with participants who all have very different levels of experience and diverse research areas, and they're coming with their different machines to work on Pawsey's system. Between us, we have a lot of experience delivering training, including virtual training, but bringing together a highly technical, highly practical bioinformatics training event to an international on a real HPC system is something special. Rather than just ring fencing a little skill or trick that you will start implementing in the real world, we hope that this session will give you an understanding of the merits and limitations of using containers in your own work and provide an authentic hands-on experience that will kickstart your own use of containers.
So the first session is about building containers. So this is quite an important component in the usage of containers. As I mentioned yesterday, bioinformatics domain is quite lucky in that there was a massive amount of work done by the Bioconda and biocontainers folks. So in the registry on the web that you used yesterday, key.io, you already find literally thousands of bioinformatics packages in a containerized form ready to use. But there can still be cases where you can't find what you need in a container, and so you need to prepare one on your own. And so this is why this session is part of the workshop. We're gonna go through at least a couple of Dockerfiles today, of recipes to build containers. I'm gonna start with a very minimal example where we are customizing an RStudio image. And then the core of the breakout rooms today will be about writing a recipe for a container where you need to compile the software yourself, which I believe is something a lot of you have gone through in the past. And here we are going to see how once you have found a working recipe for the bash shell to install software. Once you have that, you can just translate it to the container jargon, build a container, and then that software for you is installed once and forever, at least for that version of the software. So it's kind of a powerful way of saving time for your research. One key concept today is that we're going to use Docker, not Singularity, for building. And I mentioned the reason for this in the webinars. So basically, the format of Docker container images is very, very popular. Everyone has been using that for years. Singularity came later with a different format, and it hasn't really picked up yet. Also because the Docker format can be executed by any container engine, Singularity, Docker, Shifter, Charlie Cloud, whatever. Whereas the Singularity format can only be run by Singularity. So it's also a matter of compatibility other than popularity. And so it is actually worth, if one has to pick which syntax for building containers to use and to learn, the good one actually is the one with Docker. So that's why we're talking about Dockerfiles, which are these recipe files that look a bit like Linux scripts. And these are the ones you need to build containers. So we're going to review some of the concepts we saw in the webinar. So some key syntax in Dockerfiles, from to grab the base image, run to execute commands, and to define variables. And then we're gonna see what the commands you need to execute in the shell in order to build containers. So Docker build. In the exercise in the breakout room, there will be again some intended errors that will happen. And so you will see how you can kind of debug the process of building an image by executing commands using Docker run, which is kind of similar to Singularity exec. And as you're using Docker to build the image, it is just more handy to use Docker run to debug it. And then the other bit, we're doing that together in the last part of the session. So how to basically make a Docker image publicly available on a public registry online, and eventually how to convert it for actually using it with Singularity. So as I showed in the webinars, the model we are suggesting is kind of good practice for a complete container lifecycle, is to build with Docker and run with Singularity. Because Docker needs administrative privileges, so it needs to run essentially with sudo. You can't run it on an HPC, you need to run it on a machine where you can actually run sudo commands. So either your personal laptop or a workstation in your office if you have one, or a cloud instance, such as a Nimbus instance like the one that we're using today for the workshop. So the little price you have to pay is that you need to have bought tools installed, both Docker and Singularity. But in the setup page of this workshop, I have actually provided some sample scripts for installing both Docker and Singularity. So that shouldn't be a big deal. And yeah, then it might be a bit frustrating at times to write Dockerfiles. It can be sometimes a tedious process, time consuming. A bit like actually devising how to build a package even without containers. The good news is that once you've done it, you have achieved a working solution that will hold quite for a long time. And there's plenty to learn in the kind of art of building containers. So we're not covering everything today. I'm just trying to give you some key concepts, and then at the end of the session, I will also try and give you some more best practices beyond what we're going to do in the exercises. So let's start together with the first example for today. Let's write an R Dockerfile. And so the one we're going to build is actually a Dockerfile for the same package we used yesterday in the graphical example, so GG3, this package for visualizing phylogenetic trees. So if you have a look at the documentation page of this package, it turns out that it actually builds on top of other R packages that are included in the tidyverse collection. Some of you might have heard of that. Tidyverse is just a set of R packages for data science. And say one of the packages is ggplot2, which maybe some of you know is the plotting, one of the most popular plotting libraries in R. So we're going to start from an already available tidyverse image and just build on top of that. And this actually reminds me to mention possibly the first important aspect when building container image. So you never really start from scratch. You're not going to compile any operating system, right? When you build a container, it will be a bit time consuming and not really worth. So you're always going to start from a pre-existing image that we call the base image, the starting point for building a container image. And so Docker Hub, which is the analogous of Key.io which is non-bioinformatics specific, is an online registry which is really rich with all sorts of tools and softwares. And because there's the link here, I can even actually show you how it looks like. So it's a bit similar to Key.io. There is a search field, and you can just type package names and see what you get. And so there are some interesting projects in Docker Hub that provide useful base images for building Dockerfiles. So there are operating system images, so plain Linux flavors such as Ubuntu with different versions, 18.04, 20.04, and so on, Debian, CentOS. So this is basically when the package you need to build as anything special. So it's not Python, it's not R, it's not Conda. So you can basically start from a plain Linux base image. If you need, like in this first example, if you need to build an R package, there's no point of building R from scratch from one of these Linux flavors. And that's because the Rocker project provides already some ready-to-go R images, a bit like the one we used yesterday, which was based on out of one of these. So there are base R images, Rocker R-ver, RStudio images, and then there's the one we're gonna use today because it has the prerequisite packages for GG3, which is Rocker Tidyverse. And here I've just picked one version I was using a while ago, 3.6.1. So this Tidyverse image has got the Tidyverse tools, but also the RStudio interface, which is what we used yesterday in the example. If you need to build or install Python packages, there are some Python-based image, can be quite handy. There are Conda-based images for Conda fans. For people using Jupyter notebooks, there are some Jupyter images as well that can be a good starting point. So this is about just a non-complete list of useful images that you can find on Docker Hub. So now let's start and write a Dockerfile for GG3. So let's all go to our terminal in the virtual machine. We're gonna go back to the place where we were yesterday. So /data/containers bioinformatics workshop. Then we need to go again in the directory exercises, and then I think it's called build, yes. And then from here, let's go in finally in the directory rgg3. So the full path will look something like this. Okay. Right now there is just a solution directory which I'm gonna ignore. There is a standard name for images with Docker, which is just Dockerfile with the first with the uppercase D, and we're gonna follow this this naming convention. So we said we are gonna build an R package. So I would base image would be the Tidyverse one. So let's start and write this base image. So that's the first bit. So if we just we would just basically create an image which is the same, an exact copy of this Tidyverse one. Instead, we want to add at least one extra step, which is a step that allows us to install GG3 in this container. And to do that, let me go back to the browser. So I'm not an R user, so I can't really remember the commands to install R packages by heart. The thing is that GG3 is part, GG3 is part of the Bioconductor project. And so Bioconductor has got a standard way to install packages, which is this one. You use, if you are in an R console, you would run Bioc manager : install GG3. However, when we write a Docker file, we need to always remember we are to picture ourselves in a Linux shell. So we're not in an R console, we're not in a Python console, we're not in a graphical window, we are in a Linux shell. So every command that we issue there need to be working commands for a Linux shell. And so to basically turn this Bioconductor command in a shell commands, basically all we need to do is to use this R syntax. So R, the R executable, then followed by -E, and that's a way to execute. So E like execute. It's a way to make R execute commands from the Linux shell, so without opening R. And so that way we are gonna issue the installation of GG3 right from the Linux shell. So I'm not testing this in the shell because I don't have an R installation in the virtual machine. So I'm just gonna put it straight away in the Dockerfile. So how do we embed Linux commands in a Dockerfile? So there is another special instruction for that, which is run. And so what we are doing, we are writing run and then followed by this working shell command. And then, so we are almost done. So this Dockerfile, if I haven't done any typos, should be a working Dockerfile. And so I'm now closing the editor. And now I'm gonna use this Dockerfile. So I told you that we're gonna use Docker, not Singularity, for building. And so what we're gonna do is sudo docker build. Then the syntax for building requires a flag called -t that is used to provide a name for the image. So let's call it, for instance, just gg3. And then we need to provide Docker with the location of the Dockerfile. And the location of the Dockerfile is just the current directory, which in Linux jargon is just identified by the single dot. And so here we go. So there must be, so there is some typo in my Dockerfile. Oh yes. So it actually says it quite clearly, unterminated quoted string. And in fact, if I go back to my Dockerfile, you can see there is a single quote at the beginning of BIOC manager, but I had forgotten the closing single quote. So let's run the docker build command again. Okay, and now it's going ahead. So it's basically downloading the packages required for GG3 and going ahead with the installation. This should just take 1 or 2 minutes, and then at the end of it, we will have a working image for GG3. Let me just move the last bit of this guided part. Similar to what we did with Salmon yesterday. So we downloaded a container from key.io and we wanted to test that it's actually working. We want to do the same thing with this image. And we're going to actually follow a similar strategy. So we're going to ask R from the container what the version of GG3 is. So if GG3 is actually correctly installed in the container, this command should return an appropriate output. So let's copy this from the web page. As I was talking, you might see that in the terminal, the build has proceeded and the last and finished. So the last 2 lines say successfully built and then a string and successfully tagged GG3. The reason why we have here GG3 is because in the docker build command, we put -t GG3. So this name here reflects what we put there. And the latest tag is because if you don't put if you don't specify any tag in this -t syntax, or if you forget to, as I did, by default, the latest tag will be used. We're going to see how you can re-tag an image in case you want to amend that latest naming. We're going to see it later on. For now, let us just use this Docker image with sudo docker run, followed by this tagged name, so GG3 latest. And then let us paste the command that I grabbed from the web materials. So this R command to print the version of GG3. And here we go. We get some R output, and then at the end, package version GG3, and version is 2.0.4. So that's it. We built a container with Docker using a Dockerfile that we actually wrote in real time, and we ran a test command for that. Before I hand it to Anne to put every one of you in the breakout rooms for the second exercise, which is about building another tool with Docker and Dockerfiles, let me just show you one command that might be useful. So you saw with Singularity, when you deal with images, images are just files in the directory tree. With Docker, it's not the case. So if you ls in the directory or you build the container, there is nothing new. And that's because Docker actually keeps the images stored in a dedicated location that is managed by Docker itself. And so to have a look at what images are available locally, you need to run sudo docker images. And you see a few here. That's because I have pre-cached some images for these exercises to save time. But you see that the one on top of the list is actually GG3 latest. So that's how you can refresh yourself on what are the available images locally in your machine. So this might be useful in the next exercise.
Welcome back to the main session. Hoping you had a good discussion and a good, good chat. Is there anything that anyone would like to share coming out of the session? Any questions or any gotchas or anything? Please feel free to unmute.
I'd say just what's for copying and pasting. Sometimes copying code from online, your quotes get shifted.
Oh.
Or sometimes hyphens or dashes get turned into hyphens. And,
oh, yes, right. Yeah.
And then
good
punctuation.
Reminder. Absolutely.
It's a particular problem with WordPress blogs because WordPress likes to auto-format things for you.
Good point. Good
I've
point.
turned that off on my laptop because it was driving me crazy. Yeah. All right. So, well, so I hope you enjoy this exercise of writing some Dockerfiles and building containers. Let me wrap this up with you now. So just in the interest of time, you mostly focused on writing the Dockerfile and then the build process. Now I'm going to show you the last bit, the last mile to get to share the images and use them with Singularity. And we're going to use the example of the compiled SAM tools for this. So you saw I also have in my list of Docker images in my virtual machine the final image from the exercise we did in the room. So I called it the way it was suggested in the exercise, so SAM column 4. So if you want, so this format is not the good one if you want to share the image publicly. And the reason is that what you're going to do, you're going to push this image in a Docker Hub. And Docker Hub is a very specific format for naming images, and I'm going to show you how to use that. So there's a command which is docker tag that allows you to add additional tags and names to images that are pre-existing. This doesn't take any extra disk space because the image is still the same. It just gets to have multiple tags associated with it, or multiple names. So I'm gonna add a tag to SAM column 4. And the way I have to call it is to start with my Docker Hub account. So if any one of you has got a Docker Hub account, you can do the same thing. If you don't, just bear with me and have a look at what I'm doing. The account creation is free, but right now you don't really need to go through that process. It takes a few minutes out of our time. So this is the key requirement. You need to use the Docker Hub account, then / and then whatever name we want to give to the image, which can be different from the original one. So in this case, let's go for test SAM tools. And now, unlike the other time, I'm remembering to use Subversion to avoid the latest tag, which is not really good practice. It's not good for reproducibility and knowing what you're using. So let's use the SAM tools version in the image 1.9. And that's just instantaneous. It's just adding a name to the image. And now that I have that name, that's the one I can use with the command docker push, which is the one that actually performs the upload of the image to Docker Hub. And I believe the first time you run this type of commands in a machine, you actually need to authenticate in your Docker account, and so that's why it was not working before. There was authentication performed. So now we will start to push, and yeah, it will just take some time to get it done. Hopefully not too much. Meanwhile, let me show you in the web browser how we can actually see the result of the action I'm actually doing on the command line. So if we go back to hub.docker.com, so and this is actually my account. So here we go. There is this test SAM tools image with tag 1.9, and it's telling me it was uploaded a few seconds ago. So that's exactly the image I asked Docker to push on my Docker Hub account. And so you see it's now available. This means that basically I can now do things. So the image is now on a public registry, so I can do things like Singularity pool, Docker, and then the name of that image. And that's basically the same thing that we did yesterday with the other packages we've used with containers, so Salmon, FastQC, and so on. What's here? This shouldn't be happening. It must have been some glitch when I configured Docker in this machine. But no, you see that the image was uploaded with Docker push, so it can now be downloaded with Singularity, and Singularity will perform the conversion between Docker format and the Singularity on format safe. So, and basically that's what closes the loop, right? So you create your image with Docker, you make it public available, and then everyone can download it and use it with Singularity or other container runtimes. The last thing I just want to show to you again is that if in the machine where you build Docker, you also have Singularity, which is the case here, you have no obligation to really push the image publicly before you can use it, because you can just convert it in an offline fashion. And maybe just in the interest of time, no, here we go. So the image was downloaded, it's the one. We can even test it with Singularity. SAM tools, help, and here we go. And then what I was gonna say is that, let me create just a separate directory to show you this extra command. The pool it just performed was from the public registry on the internet, but because the Docker image was built in this machine, so it's also available locally, there is also an offline syntax that we can use, that is Singularity pool Docker daemon, followed by the image name. And that the difference compared to the previous command is that this is all happening offline. So there is no download from a public registry involved. We are just converting the local SAM tools image built with Docker into the Singularity format. So you have and once you have the Singularity format, you can share it privately eventually with your collaborators and so on, or use it yourself, transfer it to the machine, to the production machine where you actually need to run your containerized application. And you can see it's basically it ends up being the same process where you end up creating the zip file. Now, in the interest of time, I'm not waiting for this to be done, although it would be kind of quick, but I prefer to come back to the browser and comment a bit on some best practices for Dockerfiles. So scrolling down towards the end of this page, I'm providing you with a kind of expanded version of the Dockerfile you worked through in the breakout room for SAM tools. So you can still see there is the from instruction to start with the Ubuntu container. There are still the ran commands to install the dependencies and then install SAM tools itself. But then there are also some additional modifications compared to what you went through in the room, and I want to comment a bit on that. So the first comment is about how many run commands you should use in the Dockerfile. So if you follow the guide and the steps in the room, you might have ended up with, say, 4 run commands in the Dockerfile, or maybe a bit less, maybe 2. Well, you have some saying in how many run commands you want to use, and you can, and there are some arguments you can adopt to choose how to proceed. So, on one end, you might be willing to use the maximum amount of run commands possible. So here it might be 1 for apt-get update and 1 for install and so on. Even in the build process, you might want to use to use the run instruction for many more times that I'm doing here. So this has the advantage, possibly it might be a bit clearer to read, but it has a big disadvantage in that every time you have a run command in Dockerfile, Docker is creating an additional so-called layer in the image. And the layer is nothing but a snapshot of the files that you are actually installing in the container. So the more the number of run instructions you have in the Dockerfile, the more snapshots of these files you are taking. And if you have the more snapshots you have, the larger the size of the image has. So you will end up with a bigger image, say more megabytes, more gigabytes in size, which is then bigger to transfer and to move around. So that's one end. On the other end, you might want to reduce the number of run commands to the minimum. You might eventually just have 1 in some cases. That might be a bit more tedious to type, but it also have a drawback on the other side, because if you only have 1 layer in the image, you have no way of exploiting the caching mechanism during the build, which can be useful when you're actually debugging the build. So we'll just take more time to go through the process. And so there is a sweet spot. What is a good number of run commands to use? Well, what I'm suggesting here a modular approach. So to issue and use a run command for each installation block in your Dockerfile, and that's what I'm doing in this example. So there is a block for the dependencies that are installed with apt-get, and then there is another block for the SAM tools component, and that's it. And this is a kind of a sweet spot because the snapshots I was mentioning, right? They make multiple copies of the file every time those files are edited in different runs. But so for instance, the second bit where we're building SAM tools is not editing at all the files that were created and installed in the first bit. So having 2 runs is not harmful in terms of the size of the image, because these 2 blocks of instructions, of commands, are working on completely different files. So you don't want to really get crazy and spend a lot of time about thinking this out. It's just a kind of a general rule of thumb. If you're installing multiple components in the containers, you can use a run command for each one of them. And that's a good compromise between having a good caching behavior and having an image that is not too big. So this is one practice I wanted to mention. Another one which is quite important is cleaning your image from files you don't need for execution. And that, so that can also save you some disk space. And how to do that? Well, just a couple of examples. If you're using apt-get to install packages, the good practice then is that at the end of the apt-get process, to add some cleaning commands that apt-get has. So apt-get clean all, apt-get purge, And you can even remove some temporary files from some standard locations in Linux, and that will save you some disk space in the final image. And actually, this is also, again, a good time to comment again on this number of runs you're using. So suppose you were using a run here and a separate run for the cleaning. If you do that, you are not saving any space because Docker would snapshot the deleted files anyway in the first layer. So that's a good case where you really want to group together commands that act on the same files. So you are installing stuff and then you do the cleanup in the same layer, so in the same run. And I'm doing the same here for the CentOS bit. So after we have installed the CentOS executable in this apps folder, I'm then deleting the build folder, which is where all of the source files are. You don't need them for using CentOS, so you just clean them up. And so these two tips together, just in this example of CentOS, so using two run commands and clean up can save you, say, 30% in the final image size. There are even more elaborate ways of saving on the image size, which I'm not touching here because they take kind of a lot of time. So we need to wrap up soon. So there is a couple of just a couple of more practices I wanted to mention. So one is about a couple of useful environment variables that you might want to consider having in your Dockerfiles. So this is specific to Ubuntu and Debian. So setting env Debian frontend non-interactive. So this basically makes the build process aware that these commands are not being run by you in an interactive shell, but they're being executed in a script. And so as a consequence, if any of the installation processes need to ask questions and prompts to you, they won't do that because now the shell will know that you're not interacting with the process. And instead, the default value will be big. So this can save you from undesired errors when packages will need to ask you questions during the installation. And this one is about setting some default localization settings, so which is about the character set associated to your keyboard and to the visualization of characters in the screen. So if you don't set this up, there are some packages that might end up showing you weird characters, both in the installation phase and in the usage phase. Whereas setting up, say, a good standard such as UTF-8 it's kind of a safe choice because any package that needs some localization information in terms of the characters that it may use in the screen, it will have some default to start from. And then let's see, there's a couple more, but these three ones were actually the important ones I wanted to mention to you today.